So today's call, we're going to hear from Téo Lohrer, who will represent Dioptra's work on fast-mda-traceroute. Téo is an IT engineer at Summit, which is an engineering unit at Sorbonne University in Paris, where he collaborates with Dioptra. And Dioptra is an internet cartography research group within the network and performance analysis team at the LIP6 Computer Science Laboratory in Paris. Dioptra and MLab have been or are both committed to internet measurement at scale and have been partnering over the past year to publish new data sets, such as their Zeph data set from their IRIS project. You can find out more. I'll drop this link in the chat in a second on their website. If you're interested in a similar partnership, if you also do similar internet measurement research, or are interested in presenting your work for feedback at an upcoming community call, please reach out. Feel free to message me in the chat as well. This is something that we're interested in doing more of. And we have a lot of really bright people in the community who can provide more insight and give you more thoughts on your work. So if that platform is interesting to you, please feel free to reach out. For today's presentation, we'll have time for questions at the end, so feel free to write them in the chat as we go. I'll keep an eye on that, but Téo will just focus on the presentation, and then we'll come back to the questions at the end. Before we get started, any questions, thoughts before we go in? Okay, great. We will now do the ritual of passing the sharing of screen. Great, we can see your screen.
Yeah, hello everyone. So it's a treat to be able to present what I've been working on for last couple of months for Dioptra. So just as a warning, I'm fairly new to internet measurements and network research in general. So I apologize in advance for any approximations. So yeah. So I will be dividing this presentation into sections. So the first one is, why do we care about a new network route tracing tool? So there should be some recalls about what a route is in the internet, why we need new tools, and what we are trying to achieve. I will describe in more details the multipath problems. So how can we discover all paths between 2 points? It's not super easy, so I will go into details with that. And then I will describe a new probing heuristic that I developed that has to do with efficiently discovering all paths between 2 points. So this is the main new contribution in fast-mda-traceroute that I contributed to. And as with all route tracing tools, there should be concern about testing these tools and how do we test tools that deal with uncertainty, especially with the internet. And so how can we be sure that the FMDA implementation is correct? And then there will be plenty of time for questions. I have a lot of backup slides, especially regarding the slides, regarding the math. So please ask questions, so that would not have been in vain. Okay, let's go and motivate this talk. So historically, traceroute has been the best tool available since 1999 and until recently. And it maps IPs along a path from a source to a destination, and does that by manipulating the TTL field. And it works really well for linear paths. But even in this best case scenario of a linear path, where it gets replies from routers, it just sends a probe, waits for a reply, gets a reply, and then sends another probe 1 TTL further, and then gets a reply, etc. So this is incredibly slow, especially for long paths and complex topologies. So I just wanted to mention that while traceroute is widely used, widely available in all the Unix distributions, it still suffers from, it's still painfully slow at scale. And the internet now is not like it was in 1999, hopefully, and we now have load balancers. Here in this diagram, R0 is a load balancer that maps traffic to R11 and R12. And in this case, traceroute will get a response from R11 and then we'll get a response from R22, and we'll deduce that there is a link, an edge between those two nodes, which is not the case. So traceroute is slow, but also wrong because it hallucinates non-existing routes. So this is a real issue. Those are real issues. And so there have been efforts to tackle that and try to... Oh, sorry. Okay. Bless you.
So sorry.
No worries.
And so there have been efforts to tackle that problem and discover what we call a multipath. And there are two main innovations from Brice Augustin, Timur Friedman, which is in the call, and others. The first one is the Paris technique, which won the 2022 IMC Test of Time Award. So that's kind of a big deal. And it controls the header field in each packet that we send to get reliable single path. So if the Paris technique finds a single path, it is one that actually exists, contrarily to traceroute. And a year later, and in following papers, the multipath discovery algorithm, so MDA, was introduced. And it's a technique to discover all paths between 2 points. So this algorithm is, so there are lots of ideas and math in the papers, but it actually does not describe precisely the implementation that we should use. And so that was kind of my job at Dioptra to suggest a new implementation and to build upon the work of my predecessors. Currently, the Paris technique is widely implemented and used in a variety of tools, Scamper, for instance, and MDA less so. And yeah, so we really want to remediate that. Yeah, there might be question at the end where we are getting all our multipath route traces, but one definite source for these traces is MLabs data. So let's go a bit deeper into fast-mda traceroute. So FMDA, as I will call it, we wanted to actually implement the MDA algorithm. So that's the kind of the main point. But we also want it to be free and open source. It should be available for the community to download and to contribute to, hopefully. So that means being on GitHub or the likes. It should be legible, and that means easy to check whether the implementation is actually correct. It should be tested, so letting the machines do the checking, and reliable. And of course, it should be fast because it's called fast-mda traceroute. So in terms of legibility, for now, we have a modular design where there are kind of the brains of the MDA algorithm, which chooses which probes we're going to send at which TTL, etc., and how many rounds we're going to do, and the legs of the probing engine, which is currently coded in C++, and it's a separate project for now. The fact that it's in C++ has led to some difficulties with packaging this software and compiling it reliably on various targets. The brains for now are in Python in order to be accessible and reviewable and to be able to iterate more quickly on the software. I am currently porting all of that into in Rust. So we are compromising slightly on the legibility, but good Rust should be legible. But we will have a much better time packaging it and distributing it, and with very few dependencies. So let's go a bit more deep into the algorithm. So if we have that kind of network as displayed on the slide, we want to ask what are the nodes on this network. So I'm calling it a network really in the graph sense here. So we want to discover the nodes on this network, the edges on this network as well, which is really important. And there is really this idea of how can we be confident that we actually found everything. If I probed and probed and probed the network and I get this topology, how confident can I be that this is all there is to it and that I found everything there is to find? And this confidence idea is really key. And as we'll see, this problem is a stochastic problem, and it will be solved with a stochastic process. So I will simplify this case for most of the presentation into a single load balancer, and we'll see that it's actually challenging enough to get things going. So when we're faced with a single load balancer, we are going to manipulate packet headers to trick the load balancer into routing our probes along multiple paths. The problem is we don't know the internal logic of the load balancer, and we don't know if this field will be taken into account by the load balancer. We don't know if we don't have a sure way of finding all interfaces that follow a load balancer. We have hints, we have ideas, we have some knowledge of some routers, how they're working, but we don't have the whole picture, and it can change. So, for instance, if we send 5 probes through a load balancer, we might get 2 different interfaces. We observe 2 different events, 2 different interfaces, but there might be more. So we keep on sending probes. After 8 probes, we've found 2 new interfaces. So that's great, but there may be more, and we have no way of knowing if we found them all. And then we send a lot of probes, 20 probes, or maybe 200, and we don't find any more interfaces. But actually, when should we stop? And we want to do that in a quantitative way. We want to really be able to measure the confidence that we have in when finding all interfaces following a load balancer. So when we are probing in the wild, in the real world with the fast-mda, we are doing that kind of probing on all of the TTLs at once, in parallel. So we call this process batching, and it really puts fast into fast-mda. But we'll see that there are still some limitation. So I just want to give you a rough idea of the algorithm that we are going to be using. So given the topology on the left here, we have to make a guess on the total number of interfaces. So we'll say maybe 7. So we have an estimate on the number of existing in total interfaces. We send as many probes as necessary to confirm this estimation with a strong probability. So I can give details on that, but it's quite technical. So for instance, if you want to confirm that there are exactly 2 interfaces with a 95% probability, we will send, I think it's 11 probes. And if we found indeed as many interfaces as our estimation, we're good. We have a strong confidence in our estimation and that we found them all. So we stop and report. Else, if we found more interfaces, we update our estimate and go for another round. So yeah, just rolling back, this estimation is, of course, the heart of the algorithm. It's the most important part. And estimating the number of the total number of interfaces is what we call a probing heuristic. And I will give some example of heuristics here. So let's say that we found k interfaces. In the previous example, it was 4. We can say that our estimate is that there are in total 4 interfaces. There should not be 3 because we already discovered 4, of course, but saying that there are exactly the number of interfaces discovered at that point in total is a very conservative estimation. Actually, this heuristic is the one that was used and is still available in fast-mda, so it's very, very conservative. We could have another kind of heuristic that is not implemented, of course. It's that if we found 4 interfaces, we would estimate that, okay, we found half of them, so there should be double that number, so 8 in the example. That would allow to do less and way less rounds of probing and reaching the total number of interfaces much faster at the cost of sending way too many probes. We could also just have no estimate at all and send 32,000 probes to every TTL, 64,000 probes to every TTL. That is not a good heuristic, but it minimizes the number of rounds drastically because there is only one round. Sorry? Oh, okay.
I don't think there was a question there. I think you can continue. Yeah.
So what I wanted to give you the idea of is what we are trying to maximize coverage. So the likelihood that we found all interfaces within certain bounds, while minimizing both the number of probes that we send, and that is the work we impose on the network, and so the network cost, and the number of rounds. And the number of rounds is just us waiting for replies from routers, and that is time. So we are trying to minimize network cost and also time cost at the same time. So as you can see, the first estimate will do more rounds than the second estimate, but it will minimize the number of probes really okay. What I don't like in all of those heuristics is that they feel kind of arbitrary. So the double the number of interfaces is really arbitrary. The last one is really arbitrary as well, but the first one is also arbitrary because if we found like 20 interfaces, there should be a more informed guess on the total number of interfaces than just saying, okay, we found them all. And so that's kind of the question that we are trying to, we ask ourselves when designing a new probing heuristic here. So the question goes as follows. So we detected 6 interfaces at a given TTL. What is the most likely total number of interfaces? And when you look at that question, it kind of doesn't make any sense because it could be anything really without any prior knowledge of the network. And networks can be like very small networks, very large data center with lots of load balancers. It could be the internet. So it really, you cannot make an informed guess with just that. And you have to take into account the number of probes that you sent so far. And so I designed a formula to do just that. And so these are some results for 6 interfaces. If we have sent 7 probes and got 6 interfaces, actually the most likely total number of interfaces is 19. That feels kind of arbitrary, but it's actually there are some real maths that I'd be happy to share. And so, yeah, 19 is the most likely. Of course, if we send lots and lots of probes, 20 or 200 probes, and only get 6 different interfaces, the most likely total number of interfaces is 6. But remember that the current heuristic does not take into account the number of probes, it just says 6. So once again, details are available. Feel free to ask if that's something you're interested in. So what can we expect from this new probing heuristic? So just like the doubling heuristic, it allows jumps in probing, and so it should reduce the number of rounds of the algorithm. So that means even faster probing. Actually, the current very conservative estimate will fail on very large load balancers, and we have seen like 1,024 interfaces load balancers in the wild, and that would not finish in a reasonable time, the algorithm in its current form. But with this new heuristic, we hope it will. Potentially, it does send more probes. I have an example run for you to show, but not that much. And this is an idea that I have that I guess that it should be slightly more accurate in the long term, because it does less steps and it has that many less occasions to fail at each step. So it's kind of hand wavy, but there are some arguments, I promise you. Okay, so this heuristic was implemented in fast-mda, and it's actually quite complicated. There are many ways to mess it up, and so I try to reassure myself and reassure Timur and the people I work with by doing lots and lots of testing. And so I asked myself, how confident can we be with the implementation of fast-mda? So I'm very confident with myself, but I need to prove it to my colleagues. And so what we really needed to do was to successfully probe known topologies. What do I mean by that? If you're starting to probe random routers, random IPs on the internet, you are going to get some results, but you have absolutely no way to confirm that you are getting the full picture. You might try to compare with other tools, such as Camper, but I am not entirely sure that it gets the full picture. And I mean, if we could do better testing than this, why not do it? So I set up an environment to build artificial topologies and known topologies from arbitrary specifications. This is not like a network environment. It's all done in Python. It simulates a probing environment and routing, etc. So it's very basic. It does not implement complex hashing methods from load balancers, but it should give us reasonable confidence in the correctness of the implementation. So known topologies are super important. That should also be very different topologies. As I said, the internet is wild, and so we have like very small networks, very meshed networks, and so we should have some way to test all of those configurations. And maybe the most difficult part is defining what success actually means in this case. because we are dealing with a stochastic problem. And so we want to know how often should we be allowed to fail probing a certain network. And that's a difficult question, actually. So I will give some elements about it. So the implementation actually runs, so I set up about 250 tests. It runs in a reasonable amount of time on GitHub. And it includes artificial topologies, so really built from scratch, real-world topologies as well, and some unit tests. What kind of topologies are we testing? We are testing multi-single pass topologies. So I just wanted to test whether a single load balancer followed by long routes to the destination would work. These are normally easy topologies, so it should work, but you have to test that because you can never be too sure. Meshes, which are networks where all nodes at a certain TTL are connected to all nodes at the following TTL. And also random networks, so that there should be quotes around random, because currently there are always balanced networks where all paths from the source to the destination are the same length. And also, yeah, I'm doing real-world networks. So from specifications, not probing in the wild. And just wanted to give you a quick view on the implementation. So it's using PyTest and parameters. And so if I want to extend my tests of meshed networks, I can just vary the height, so the number of nodes at each TTL, or the length, the number of TTLs. And I actually did that on my machine to have like really big mesh networks to see if that behaves correctly, and it does. And so extending these tests is really easy. I did not write 250 tests by hand. These are generated like this. The optimal jump parameter is whether or not to use the new heuristic. And so, as you can see, I don't know if you can see my mouse when I highlight stuff, but I'm instantiating a fake net here, which is a Python object that I can use to fake probe with my algorithm. So what does success mean here? So we have some idea of what success means with a single load balancer. As I said, there is some number of probes that when we send them to a load balancer, we can be fairly certain that we reach each and every interface. But that's not the whole picture, because when we are probing, we are doing that iteratively in rounds. And so we can fail at previous rounds, even with very low probability, but that can happen. So what I mean is that we have to take into account the confidence level, as I said, but also the topology of the network as well. But also, and that was new to us, the probing heuristic that we are using. If we're doing lots of small rounds, there are some marginal probabilities that add up to fail at each step, even for a single load balancer. And I'm not even talking about large networks. So the a priori success estimate depends on what we are doing locally, the topology of the network, and also how we are probing. So computing this a priori success estimate is very important for testing, but this meant re-implementing the whole probing logic in this simulated environment. So this is very, very useful to check the correctness of the implementation. And we can check whether we are within bounds of what is expected of the performance of the algorithm. There is some code and an example if you want to see. So I'm nearing the end of the presentation. So what am I doing now? So I'm working, as I said, on the Rust port of some stuff. So I'm still waiting for more validation before porting to Rust some trickier parts. We may need additional tests. There are some tuning that can be done in the new heuristics. So I'm currently discussing that with Timo Friedman. And hopefully we could get some user feedback on this tool. This is really important because I'm more of a research engineer. I have a background in software engineering and developing complex software, but it's lonely out there. So I'm really hoping that there are some people that are super skilled and maybe or just interested and will have some ideas and some remarks on the code. Yeah. So these are so there's a traffic cone sign and a warning sign on this slide. It's really important. I could have put more, but this is really a pre-alpha territory. So it works on my machine. I've successfully installed it on other machines and other servers. But yeah, be mindful of what you're doing here. So the project is available on GitHub. It's currently in a pull request. So you can clone it, go to the correct branch, and then installing and running it using Poetry. As I said, there are some issues with the CPP probing engine. Hopefully it works. I've heard it's difficult on Ubuntu 24, but on Ubuntu 23, for some reason it works. So yeah, it motivates me to port it to Rust all the sooner. And yeah, so that's it. Just the main takeaway points is that we are in a network universe where there are multipaths. We need stochastic probing. Now we can correctly estimate the size of load balancers. We can test our implementation with a priori success estimates. That's really important. And the fMDA is open for contributions and ideas. And don't hesitate to reach out at this address and on Slack. Thank you very much. So there are lots of questions. I did not look at them in advance to prepare. Oh, hello, Kevin. So yeah, there's no graphical user interface. Yeah, so sorry about that. So Ethan asks, so we have some prior knowledge of networks in general and networks that we have already scanned, I think, and sorry, and using okay, and what does that give us? And does that change the work of the algorithm? Okay, so the algorithm relies on heavily on a single formula. Oh, sorry. That's here. So and this formula tells us the probability to observe a certain number of interfaces. given a total number of interfaces and the number of probes that we sent. So it's really easy to update this estimate with external sources, including prior knowledge. So we would not start from scratch. I don't know if that answers your question. And also there is a second question. Okay.
Thanks. So this is Ethan. So just to quickly look at this, so where would you put in that previous estimate, and what would happen? I guess if it changed, it's fine because it's just estimated anywhere. So which variable do you sub that in for?
Okay, so here we have an example run of the new heuristic. So I'm sorry for the LaTeX formatting here, but so we have an estimate on the number of total interfaces. And so we get the number of probes that we want to send, here 6, to confirm that we have 1 interface. And so we have to send 6 additional probes. We send those 6 probes and we get back 5 total interfaces. We update then our estimation.
Yeah, so I understand this in general. So let's say you finish this in one traceroute and you discovered 29, right, after round 4. Then yes. Let's say a day later, I'm measuring again. Most likely it's still 29, but maybe it's changed. Can you then just substitute 29 into the first round current estimation? And yes. It will tell you, okay, great, thanks.
But I think in real world, we would probably put 28. Or maybe because interfaces can evolve up or down. So we would maybe aim a bit lower and have maybe one more round. I don't know, but yeah, we could bootstrap the algorithm. And so the second question was about equal cost multipath in calculating the probabilities. So I assume you're talking about load balancing with even probability distribution.
Yeah. Is it assuming it's uniform, and then what happens if it's not actually? Is it safe to assume that what happens if it's not? And then Lockman asked a follow-up question, more detailed version that you can look at in units.
So what we are doing, so we take into account non-even load balancing, and what we do is that in the computation, it does not in this kind of computation, this kind of stuff, it does not change anything. But when we are saying that we want to send like 200 probes to this through this particular router, we are checking what proportion of the probes we sent at that TTL actually go through that router, and then we divide by this proportion. So the implementation works with non-even load balancing. Because even if we have even load balancing, maybe I'm saying something. No, I think that's correct. Just topologically, you can have a non-even path. So yeah, it works. So Lockman's summation, can you explain a bit? Assumption you are making that the load balancer is so yeah, so I think I kind of answer that. So the assumption is that the load balancer is consistent, and when we are sending exactly the same probe, it will route it the same way every time. Yeah, so that's a key assumption. Another one, there might be other one, but it's not related to the evenness of the load balancer. Did you have any other assumption in mind?
Yeah, the one thing I was wondering is if you it can be hard to know when you are supposed to. It can be hard to know if you're not seeing a path because it's just a very unlikely path. And so I would like with your probability estimation, it seems like there is an underlying assumption of evenness such that, you know, if you run this number of probes and you don't see any other interface, that means that the likelihood of this existing is very small. But what if you're like in an uneven case? I guess I don't fully understand why it doesn't work, but maybe I need to think about it. Maybe it's not something you can answer on the. It's more.
Let me think just a second about a single load balancer with like one very unlikely case.
Yeah, exactly.
No, actually, you're right. It would not find it. But then again, who would?
Yeah, and I think maybe there's an argument, like a claim to be made that what you can say is you can find the load balancer that are used for 99% of the path or something like this, so that it's not about, you know, finding all the interface, but more finding all the interface associated with their with like the path and how often they are used.
Yes, yeah. So I guess when we are saying like I will, with that many probes, I will find all the interfaces with a 95% probability. I guess you could turn that around and it's assuming, yeah, actually it's assuming that they are evenly load balanced. I think Kevin might know actually.
Yeah, I guess, yeah, if you have an even distribution, it's harder. Like it's another problem.
Oh, okay. So Ethan, so that's not a question for directly for me. I can answer of what I plan to do with this tool. So what I plan to do is test it more and more because I'm really paranoid on the implementation and the correctness of the algorithm. There are some tools out there that are quite difficult to get to understand very finely, just because of the size of the code base or the language used. And so the objective is that with traces gathered by MLab through this tool, we can be more and more sure of the correctness of this tool. And yeah.
Yeah, and I can add to that, Ethan. The way that I would characterize it at this point is that we are an interested stakeholder and helping facilitate collecting data to be able to do these comparisons. But this isn't meant to be we don't have plans for this to be long term at the moment. This is just testing it right now. Does that answer? I think there's a second part to your question that I also am not necessarily the person to answer in terms of long-term support for the tool.
Yeah, thanks. Yeah, I think it would be super useful in the short term to issue, I'm not sure what the current trace routes, if they're Scamper or what, but to issue them in parallel and just understand, are they uncovering different things and what's the cause of the differences?
Yeah, that's exactly the intent of the current trial. And it's Scamper at the moment that we're running.
And for the support in the long run, so currently I'm actually a contractor for Dioptra, but I feel that, and my experience says that as well. If you set up a project correctly with super tight tests and clear documentation and community engagement, it can maybe becomes self-supporting. So that's kind of the idea here, but I'm not going anywhere.
If I could interject for a moment, the reason, pardon me, the reason that we contracted with the Summit unit at our university on this particular work is that Summit is a unit that's devoted to supporting free open source software that comes out of the research groups at the university, and that is destined for the wider community, and providing long-term support for such software. And so, as many of you who are in academic research teams know, it's hard to maintain software with a rotating cast of doctoral students and postdocs and so on. And so here we have the support of a professional software unit at the university who will help us maintain it over the long term.
I would like to add a footnote to that. One of the things that has killed some projects is not having adequate enforcement of review standards. And if you design it perfectly, you have good tests, good documentation, and everything works. And then somebody adds a really cool feature that turns out to conflict with some combinations of selected features. And if it doesn't get discovered and it gets into the release, then you cause problems later on, because you can't necessarily test all the cases. And so making sure that the test coverage is complete for the combinatoric product of all the feature spaces is actually very hard. And enforcing it is even harder because it gets political.
Yeah, what I currently aiming for is just lots of functional tests. There are actually not that many unit tests right now, but I feel that this is what would really motivate the community to engage with this tool, is like kind of being certain that it does what it says correctly. And so testing lots and lots of topologies and doing that not by setting up artificial networks and that kind of stuff, just doing all of that in RAM and in a auditable way was really important. I hope to also see maybe contributions or contribute myself to the CI/CD path, but currently I'm seeing fast-mda-traceroute, the Python version, as kind of a very elaborated draft for the Rust version.
And I don't know if you saw, but Ethan had one more question about the trade-off of building the tool versus building on top of Scamper.
Okay. So Scamper is quite daunting to get into, at least for me. So I think one of the difficulties I faced when trying to understand what Scamper does, and ultimately just I only had a superficial knowledge of what Scamper does, is that it does everything and has no dependencies. And that means, at least to my superficial knowledge, that some parts of the software are really intertwined, and that made it a bit difficult for me to get into. fast-mda, I did not write the first version at all. It actually has been around for 2 years. And so I had at my disposal the original developers. And so I could ask questions on this. And as you've seen, there is some math involved here, and I felt much more comfortable doing that in Python. So all in all, I wanted to contribute to the in-house tool of Dioptra and not directly to Scamper. But that does not mean that it has been the case in the past where ideas from one tool were ported to another. And actually, the more the merrier. there were also some really precise stuff that that bothered me a little in Scamper. For instance, the confidence parameter is 95 or 99, and that's it. I think you cannot put any other value. Correct me if I'm wrong. And the values for the stopping points are hard-coded. So it helped me actually find bugs in my implementation. So thank you for that. But that bothered me a bit. In fast-mda, I actually modified the code so that you can put floating point values for the confidence and have 99.999%. And this is thanks to actually this formula, which is a direct formula, not a recursive one. And it allows us to compute the stopping points on the fly with a cache, of course, but we don't have to put like a very big cache and very large tables of pre-computed values only for certain values of the confidence parameter. This is all personal, and it's not a. I have much respect for the size and the performance of the tool.
Any last questions before we close out? This has been a very productive session. Any last questions? Téo, if you want to go to your last slide, or just to make sure that people have a chance to get your contact info if they want, or you could drop it in the chat. And I put the slides in as well. I think we'll send out a PDF version too. But Téo, thank you so much for such an in-depth presentation, and everyone for your questions. I will post the recording on YouTube shortly after today. So if someone you know might be interested and couldn't make it, they can view the recording. We have these calls every month. Again, if you're interested in presenting some of your research, or are interested in seeing some other forms of information about MLab or anything internet measurement related, please feel free to reach out. But thank you all for joining, and have a good rest of your Thursday. Thank you.